All right, more of the same. You can do this in your head now, right? Okay, so for the first one, what do we get? No. F prime of x equals minus 4, and that's it. How about the second one? G prime of x equals negative 2x to the third. Good. We good? Yeah? Okay. Derivatives of trig functions. We will eventually get to more than just sine and cosine, but by and large, we will be working with sine and cosine the most. You read the section ahead of time, even though we're almost done with the section? So you read it last night? Okay. Well, we're going to go through why, because probably you know what they are. You could have just looked in the inside cover of your book, right, and learned it, but let's go through why. So we have sine x, here's the graph for it. We have cosine x, here's the graph for it. We're going to estimate. It's kind of a sloppy way to prove something, but that's how we're going to do it. We're going to do some estimations here of the derivative at various points along the way for each of these. What does it look like the slope of the tangent line for sine would be at 0? About 1. Okay. So I'm going to put a dot right here. I'm going to graph the function that is the derivative of sine. Okay. Over here at pi over 2, probably the derivative would be what at pi over 2? 0. So that would be pi over 2, 0. Now back at pi, what would the slope of the tangent line there be? Looks like about negative 1. So here we are. And how about 3 pi over 2? 0 again, so here we are. And then finally at 2 pi, looks like about positive 1 again. And if I draw this graph, it looks like cosine. Okay? And in fact, the derivative of sine is cosine. Let's do the same thing for cosine now. If we start at 0, the slope of the tangent line there would be about 0. Then we move over to pi over 2, the slope there would be, okay, so a negative 1. And then we move back to pi, so the slope there would be, we're at 0. And then we go over to 3 pi over 2, the slope there seems to be about 1. And then we go to 2 pi, and the slope there seems to be back to 0. So if I draw this graph, it does look like sine because we're going through the origin, but sine looks like this. It goes up first. This one's going down first. In order to do that, you have to reflect it, which means it's going to be negative sine x. So that's not the greatest way to prove this, but it is a nice visual way to remember why the derivative of sine is positive cosine. The derivative of cosine is negative sine. Okay? We will be working with trig functions a lot in this class, so you need to have these memorized. So it's as simple as remembering what the derivative of the trig functions are and then applying it. Find the derivative of y equals 2 sine x. The derivative of sine is cosine, so it's just y prime equals 2 cosine x. That's it. That constant in front of it stays there. Kind of like when we're taking the limits, we can pull the constants out and then take the limit and then put the constant back in. Same thing happens here. Sine x over 2 turns into y prime equals what? Cosine x over 2. Technically that would be 1/2 sine x, so really we have the exact same problem as the first one. And how about the last one? So that would be y prime. Remember, this is an equation. You need to write the full notation. It stays an equation. I take the derivative of this in parts. The derivative of this term is 1. The derivative of positive cosine x is negative sine x. So that is the answer, 1 minus sine x. Okay, the last little bit of this section deals with rates of change. The rate equation you learned a long time ago, Mr. Bowe's class or something, d equals RT, right? So if I take d equals RT and I solve for r, the rate, I wind up with distance over time, right? Okay. What is the equation for average velocity? No. Yes. Yeah. Yeah. That's pretty much right, yeah. The equation for average velocity is you find out how far you went in that certain amount of time, right? What is your average velocity between here and here? You'd find out how far you went and divide it by how long it took you to get there. How far you went is a, and how long it took you to get there is a, average velocity is nothing more than this equation. But the way that we just worded that sounds more like the slope equation, right? Okay, so average velocity tells me that if I find the change in distance and divide it by the change in time, I wind up with my rate, which is exactly what I have right here. The change in distance divided by the change in time. If we put this in terms of what we usually work with, x and y, then this would be delta x over delta y. Which we know as, right? No, I have it backwards. It's the other way around, isn't it? dy over dx. If you graph this, you usually put time on what axis? y2 minus y1 over x2 minus x1. Sorry, I'm just a little confused today. Delta y over delta x. So what can we say? Rate is average velocity? So average velocity, I just wound up with that. The rate is a derivative. Yeah. Of what is the question? No. Average velocity is sitting right here. That's my derivative. Where did average velocity come from? I took the derivative of something. What did I take the derivative of is the question. No. Stop. How far you went is a what? Not a distance. Think in terms of physics. I have velocities. I have accelerations is another one. I have one more. No. 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 That's velocity. I have acceleration. And in that same realm of problems, there's one more thing.
Come on, physics guy. Go.
It's a word for distance. Like you could think of it as a word for distance. Not displacement. Not vectors. Starts with a P. You're killing me here.
The confidence part.
Relates to distance. No. Starts with a P. You do. I know you know it.
Are you just going to let us flounder until
Position.
Position. Based on what we have sitting right here, if we have a position function, we can find the rate of change, meaning the velocity function, by taking the derivative. All right. As I recover from my pain, let's continue. Velocity function is the derivative of the position function. You were never told that when you took physics last year, but it is true. You were basically in physics just given formulas and said, here's the position function, here's the velocity function. The general position function is this guy right here. We use the letter S to represent position. I don't know if they did that in your physics class or not, but generally in physics we use the letter S for position. No? I'm pretty sure you did. You had to. The general position function is this. 1/2 times, what's that G probably represent? Gravity. So it would be acceleration due to gravity, yes. T is probably time. V naught is probably which velocity? Your initial velocity. S naught is probably initial position. This is the position function. So your initial position. This is the general position function for free fall motion. Okay? Generally. Normally you would get problems that involved an equation like this in free fall, and you would see negative 4.9 t squared plus blah, blah, blah. Okay? There is a reason why that negative 4.9 was there. Because it's 1/2 g. The plus something t, there was a reason why that number always matched your initial velocity. And the plus s naught, there was a reason why that number always matched your initial height. Okay? It comes from this. Let's find the derivative of s of t. I'll get you started. It's s prime of t equals. Go ahead. Why are you taking the limit? You really want to live your life in chapter 1?
Oh, yeah, we can just...
You already did it. What do we get for the first term? The 2, what's the variable here? T is the variable. G is a constant. So this is a number sitting here. The 2 comes down, we multiply it times that number. 2 times 1/2 times G is just G. 1G. T plus V naught. Is that it? That's it. And S prime of T is the derivative of the position function, which means that this is actually the velocity function. If you think back to physics, you were getting velocity equations that looked like this. Acceleration times time plus the initial velocity. I guarantee you, if you look back in your physics book, you will see this equation sitting there. And this is where it came from. Okay? So that's it. Now you have a velocity equation and you know where it comes from. So now we can give you problems where you're standing on top of a cliff and you puke off the cliff, and you can determine how fast it is moving when it hits the ground.
It's not doing anything with airplanes, 'cause I got, like...
So let's apply what we just learned. A diver jumps from a springboard that is 32 feet above the water. The diver's position is given by S of t equals negative 16t squared plus 16t plus 32. This is basically straight out of the physics book. Look at this negative 16 here. What is that? It's not gravity. It's half of gravity. 1/2 g, right? In feet per second, that is gravity, 32, negative 32. Where did this 16 come from?
That would be our
That is V naught. And where did the 32 come from? Okay. So now you know where all that stuff is, right? Where it comes from. When does the diver hit the water? How could I figure that out?
When your height is 0.
When position is 0, the diver will hit the water. So what will I do? Yeah, this becomes 0 right here. So I go 0 equals negative 16t squared plus 16t plus 32. What can I do? Yeah, how about we divide out a 16, since there's a GCF here of 16. Yes, you can factor out a 16, but then you can divide it out and get rid of it completely. How about we make that a negative 16, so that our leading coefficient is positive? So that becomes a what? T squared minus t minus 2 equals 0. Now what? Now we factor. So we need two numbers that multiply to give me negative 2, but add to give me negative 1. Don't really have a lot of choices here. What are they? 1 times negative 1 is negative 1. Negative 2 and positive 1. T minus 2, t plus 1 equals 0. Check it. Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. We're good. So solve for t, right? Zero product property. This becomes t equals 2. T equals negative 1. Now what? Think about that in terms of the problem. It can't be t equals negative 1. That doesn't make sense. Okay? So t equals 2 seconds. If you jumped off a cliff 32 feet above the water, it would take 2 seconds to hit the ground. What is the diver's velocity at impact?
So now we gotta find the derivative.
Okay, so find the derivative. What will I write? S prime of t equals negative 32t plus 16. Now what?
Oh, now we gotta plug 2s.
Yeah, because that's going to give me a velocity. If I plug the time in here, it will give me a velocity at that current time, right? As soon as we smack the ground or the water or whatever it is we're doing. So I go S prime of 2 equals negative 32 times 2 plus 16. So this is negative 64 plus 16. So S prime of 2 equals negative 48 what? Feet per second. And that negative sign basically just tells me that I'm what? Going down, because my coordinate system here was set up as positive x to the right, positive y up. But I'm falling down. So that's why I wound up with a negative answer. Okay? I'm going to do lots of problems like this. AP loves to give problems like this. They're going to pop up a lot in this chapter. So make sure you understand these two ideas here, the position function and the velocity function.